when we are in the very first beginning, which is the major topic today, and we do not know any parameters from the network, we have to estimate it, or you want to know which ratings can be expected. Actually, for our generator circuit breaker calculation and the short circuit calculation, we need certain requirements and certain input parameters. These are the detailed generator datasheet. We need the single line diagram with the mode of operation. We need a transformer datasheet. And of course, we also need the information about the high voltage grid. So if we do not have this information, what should we do then? And especially in the very first beginning, where you only need an indication. In this case, we will most likely we only got information about a single line diagram, a very simple single line diagram, and maybe the power and the rated voltage of the generator. But there are also other requirements which have to be considered. So maybe you have an IPB connection. You need to consider certain reduction factors for altitude, for the temperature, but you also need to know which rated current, which short circuit current can be expected. And that's why we have developed and published on our webpage the GBS short circuit estimation tool. And we proudly want to present it today to you so that it can be used for you as a really simply rough estimation, what can be expected. And of course, most important, with this information, you can directly come to us and you get a first indication price, what you can expect. And for this, we have prepared a video. Perfect. Now you've got the very first information how to estimate a generator circuit breaker in less than 5 minutes. We have introduced you our short circuit estimation tool, but now you may raise the questions, how do we get this information? Are these information based on real type tests? And how do we deal with this information? Actually, I want to highlight on 2 parameters which are really important for a generator circuit breaker dimensioning. First of it is it's the subtransient reactance of the generator itself. The subtransient reactance will influence the peak current and it will influence the breaking current which is needed for the generator circuit breakers. So I have 2 examples here. The first example is having a subtransient reactance of 30%, leading to a peak current of 107 kA. On the other hand, we only see a slightly higher subtransient reactance of 2%, so leading to a subtransient reactance of 15%. And we already have a lower peak current by 14 kA. So for an IEC circuit breaker, this would mean that we can deal with 2 different ratings. So on the one hand, we would recommend a 50 kA breaker. On the other hand, we would only recommend a 40 kA breaker. But for a generator circuit breaker switch here, as we are talking about a higher peak factor the generator circuit breaker are tested with, a 40 kA generator circuit breaker would be applicable and would be suitable to fulfill and to withstand the peak current and to fulfill, to interrupt the short circuit current, which is fed from the generator. Then, of course, the very well-known armature time constant. when the armature time constant is mainly dependent for the arcing time. So if we consider also two different examples, we have an armature time constant of 200 milliseconds on the one hand side and 300 milliseconds on the other hand side. This could lead to a significant difference in the arcing times itself. So this is actually pretty important, and that's why I want to highlight the importance of getting these real detailed generator data that we can use for our internal calculation to provide you the best fitting solution for your application. And of course, as we can see here, for 200 milliseconds, we will only have an arcing time, which is 25 milliseconds. And for 300 milliseconds, we are already in the range of 45 milliseconds for vacuum. That's why only a slightly difference in armature time constant can lead to a huge, bigger arcing time. So this generator circuit breaker estimation tool is based on a certain experience we have gained over the last years. We have collected multiple of generator data and put them into one big bubble and one database. What we can see is, in this case, the power versus the sub-transient reactance. What we can see is that we have a cluster of sub-transient reactance up to a power of 100 MVA, which is between 15% and 25%. And also, what we can see is that the sub-transient reactance increases when the rated power of the generator increases. But this does not mean that the breaking capability of the generator circuit breaker will also be much higher than expected. So, of course, you will need a higher breaking current, but we are confident enough with the Siemens GCB and GBS portfolio that we can fulfill the ratings up to a rating of 500 megawatts. And also, we have highlighted the power versus the armature time constant. The armature time constant, as I said, is responsible for the arcing time, or mainly responsible for the arcing time. And what we can see is that the armature time constant will increase with the power. Of course, this is mainly dependent on the generator manufacturing process and cannot be changed. So we cannot simply say a certain power has a smaller armature time constant because this is fixed together. And then what we can see is that we can see the relation between the symmetrical breaking current and the DC percentage. So this means that we have, of course, between 0 and 20 K of symmetrical breaking current, we have a huge cluster of DC percentages up to 120% maybe, roughly 120%. And then if we have a higher symmetrical breaking current, this will lead, of course, slightly higher DC percentage up to a value of approximately 130%. It's good to know that our generator circuit breakers are all type tested with a DC percentage of 130%. So what we can give to our customers, what we can give to you, is a portfolio solution which is completely fulfilling the the standards, since it is type test latest applicable standard. And then a last slide I want to show on these data which we have collected is that we have the power versus DC percentage and the power versus the symmetrical breaking current. What we can also see is that we have, again, a huge cluster of the power versus DC percentage up to a power of 100 MVA, which is also in the range from 100 to 120%. And then it kind of saturates, and it does not increase anymore. So it's set at the percentage of 130%. So as I've said, all our generator circuit breakers are type tested with 130% of DC percentage. So we can give you a reliable recommendation which generator circuit breaker and which solution from our side is suitable to fulfill your needs. And then we also have the power versus the symmetrical breaking current. Again, of course, if we have one cluster for the DC percentage, we have also one cluster for the symmetrical breaking current. Up to 100 MVA, we have we need a symmetrical breaking current for a generator source short circuit current up to 20, 25, 30 kiloamps. And then it will increase, it will slightly increase to a certain value up to 50 kiloamps. But again, we can give you a perfect solution for your needs. Of course, this estimation tool only covers a no-load calculation, because we cannot, or the estimation tool cannot deal with the transient behavior of the short circuit currents. And there we have actually two exceptions for it. So the first one is a generator in service. So we are talking about overexcited and underexcited operating points, where we have the internal voltage smaller or bigger than the applied or the rated voltage of the system. And of course, the generator either works as an inductance or as a capacitance. So this special characteristic of a generator in service cannot be covered by this estimation tool. We are using. Okay, another exception for this estimation tool. So let's imagine we have our generator running with its voltage on the one hand side, and the generator step-up transformer in series with the grid voltage on the other hand of the generator circuit breaker. So what will happen then is, due to commissioning errors, we have a wiring mistake at the generator circuit breaker, and the tripping signal will give a tripping command to the generator circuit breaker to close on a false synchronized voltage. So we have another phase sequence, for example. This will lead to a so-called out-of-phase current, having a certain and a very special transient characteristic of the out-of-phase current. The out-of-phase current is mainly dependent on the out-of-phase angle. The IEC IEEE standard, which is applicable for a generator circuits, requires a type test with the out-of-phase angle having 90 degrees. Of course, then let's come to an end. I want to give you the conclusion about this estimation tool. The estimation tool is technically compatible, has a technical compatibility with more than 500 entries of real and existing generator data, and it gets more and more every day. So the recommendation you get from this estimation tool is based on fully type-tested circuit breaker solution and GBS solutions implementing vacuum interrupting technology. And it also covers the simulation experience we have gained over the last multiple years. Of course, this tool is learning every day. So if we are feeding this tool, what you can expect if you do, or if you will get an estimation today, and you will have another estimation 1 year in the future, this can lead to slightly differences, but not because it was a false recommendation, but only because it will learn. So you will get a better estimation the longer it, or the more frequently it will be used. What I have to say is that this quick estimation tool does not cover and does not replace the required short circuit analysis, which is required by the standard. But as we are only talking about the indication phase where the input parameters are not clear, we can give you a first expectation which GCB and switchgear ratings will be expected. So if you need, or if you go further in your project, you can directly contact us to provide you this detailed simulation, which will then be transformed into the most sustainable, the most reliable, and a tailor-made solution from the Siemens GBS portfolio. And now I want to welcome back on stage Hong Urbanek for our Q&A session.
Nice. Thank you very much, Fabian, for the very informative and interesting session so far. And I just got a few questions from our audience, and I would like to address them to you. So the first question I got here is there any differences in short circuit calculation between SF6 and vacuum?
Basically, for the short circuit calculation itself, there isn't any difference, because the standard, the IEC IEEE standard, which is applicable for generator circuit breakers, does not have any difference, or that does not give any difference between SF6 and vacuum. The only thing we have to consider is, of course, the mechanics, the mechanical opening time, for example, for vacuum and for SF6. But this is not interrupting medium specific, but only circuit breaker specific. So, of course, having a different kind of mechanical opening time, or a longer mechanical opening time, will lead to a certain other amount of a breaking current and DC percentage. But the standard does not make any difference between it. And also good to know is that there's also no specific test requirement given in the standard for vacuum and for SF6. So both switching medium has to fulfill the same ratings, the same test procedures.
Okay, nice, interesting to hear. Another question coming in is, are you using open source ATP, AMTP software for your transient simulation as it is required by the IEC IEEE standard?
No, we are not using open source software, but we are using a commercial software, which is the PSS Netomag. This has the same features as other open source softwares as ATP, EMTP, and where we can do the same calculations as it is required or as is required by the standard. And also we will get the same output as for ATP and EMTP.
All right. Another question regarding the calculation. How do you consider arc voltage in your simulation?
The arc voltage is very important. The IEC IEEE standard requires to consider the arc voltage characteristic of each circuit breaker in our short circuit calculation. So when we have our contact opening, as I said, there is this arc voltage built up, and we have to take into account this arc voltage in our calculation. Of course, this is different as for SF6, and that's why it is so really important. And then we have also to differ between a no-load operation, so the generator is running a no-load without any fault location when the generator is in service, and the generator in service. So when we consider, when we calculate the generator in service with the short circuit calculation, we also have to use at least 300 volts if we do not know the specific arc voltage at the fault location. This is also required by the standard. Of course, as we know, the arcing, the armature time constant is mainly dependent on the x/r ratio. So if we have a higher R, which is the arc voltage at the fault location, will lead to a smaller armature time constant, and thus it will lead to a smaller arcing time generally.
Okay, so the 300 is given by the standard, or is this is a Siemens specific value?
The 300 volts is given by the standard. This is the minimum value. So when we are using the 300 volts as given by the standard, we are still calculating the absolutely worst case.
Okay, interesting. Can you give more insights on outer phase calculations?
Sure. The outer phase, what I've said is that the outer phase is only important for the fault synchronization. So the IEC IEEE standard only requires a type test with an outer phase angle of 90 degrees. But there might be some cases where the outer phase angle can be up to 180 degrees. Very important for an outer phase calculation is to get the very detailed, the full information about the whole system. This is the generator. This is also the transformer, the high voltage grid, and of course, mainly dependent on the outer phase behavior is the inertia constant of the generator. So if we have to calculate the outer phase current, we need to know actually everything of the whole system.
Okay. Another question regarding the database. How long have you been building the database? Does it cover specific machine types?
Oh, the database was built initially, I guess, 8 years ago. It covers the steam turbine generators, gas turbine generators. It also covers synchronous condensers, generators for hydropower plants. Of course, we have a very detailed overview of all kinds of generators which are used for generation applications.
Okay, so basically every dots you showed in the diagrams before, it's like from each and every type of,
exactly,
let's say, standard generation application. Okay. Is it able to check the DC components also in the estimation tool?
Unfortunately, this is not possible because to check the DC percentage, we have to know the detailed generator data because the DC percentage is calculated due to the transient behavior of the short circuit current. And as I've said, the transient behavior cannot be covered by the estimation tool. And that's why if you directly come to us, you contact us with the generator data, we can easily calculate the DC percentage and present it to you.
All right. All right. Um, Another question is, what is the impact of parallel generators at the same bus bar? Is it covered in this estimation tool?
This is also not covered by the estimation tool, but it can be simply calculated. Important is to know the total amount of generated power. So let's imagine we have not only one generator, but maybe 2, 3, or 4 generators. We have to calculate each short circuit current of each generator. So what you can do, of course, which is not so quite useful, but to take this estimation tool for each generator and kind of sum up all short circuit currents. But as I said, not really useful, and but it's very important to know for a multiple generation feeder to consider really each branch, each generator branch.
All right. Is there any limitation when considering parallel generators? Like, because I remember that in this dual code standard, they mentioned something with the 10 MVA limit. How is it covered here in this parallel
Okay,
generators?
I guess I got you. This is the IEC IEEE standard only covers a generating voltage above 15 MVA. So if we have a multiple generation network and we have, for example, 4 generators all having only 3 MVA of power, this will be a total power of 12 MVA. So the IEC IEEE standard is actually not applicable for the small amount of power. This is actually the same as having one big generator for 12 MVA or 4 small generators with 3 MVA. These two powers are not covered by the standard.
Thank you so far, Fabian, for the questions. We got a few more now in our checkbox, but I think we are out of time right now. And I would really ask you to answer our audience the questions coming in via email. So please, we will come back to you and respond to your questions after the sessions. Thank you very much.
Thank you for joining. Have a nice day.